In this video, we'll talk about error bounds, which is the idea of I'm doing an approximation here. How good is my approximation? So the idea of the error bound is basically that it's sort of verifying how good our approximations are to find these integrals, or really to finding anything in math. Error bounds are a common theme across lots of areas of math. We're trying to say, I didn't do this exactly because I couldn't. I did an approximation to it. How good is my approximation, and is that okay for the problem I'm trying to solve? So what is an error bound? It's a way of saying what is the worst case scenario for how far off my answer could be from the actual answer. And so we know for the most part these numerical approximations are going to be wrong, right? If I take a function and I approximate this by trapezoids, I know I'm missing the little bits of area that are in here. So my answer is going to be wrong. The question is, how far off is it? And is it far enough off that I can't use this for solving my problem? So error bounds let you say, here's the worst it could be, so I know what I'm doing, right? If I can say that the worst it could be is my error bound is within 0.001, then I know I am exactly correct within 2 decimal places. And that's sort of the way you want to think about these sorts of things. So if my error is less than 0.001, then I know for a fact my first 2 decimal places are correct. And so I can use those first 2 decimal places to be this answer because I know that it's right up to that point. So what do I get for these formulas? Well, I get formulas that involve derivatives. And you could probably have guessed that because why is my graph not a straight line? It's because it's curving or it has a second derivative. So here's what I get for my error bounds in all these different cases. So for midpoint and trapezoid rules, I need to assume my function has 2 derivatives where I'm doing this calculation. So assume that my second derivative exists on the interval from a to b, and I have some number k2 that's bigger than the second derivative across the entire interval. My second derivative is not bigger than this number. Then I can bound the error of mn, and by that I mean how far off is mn from the actual integral. I can bound the mn one by k2 times b minus a cubed over 24n squared, and I can bound the error in trapezoids by the same thing, but over 12n squared. We'll talk about what this means in a second. Let me write out the Simpson's rule 1 and so we can see how those compare, and then we'll discuss them all at once. For Simpson's rule, I need to assume that the fourth derivative exists on this domain, and that I have some number k4 that's bigger than the fourth derivative everywhere. Then my error in Simpson's rule is bounded by k4 times b minus a to the fifth over 180 n to the fourth. So what do these formulas all illustrate? Well, they all illustrate the important fact that as n gets bigger, my error gets smaller. That's the important direction these all should go, right? As I take more rectangles and more parabolas and more trapezoids, my error should get smaller, so I'm doing a better job of approximating this integral. Furthermore, Simpson's rule is a better method for doing this approximation because it gets smaller faster than the other two, right? If I take n to be 10 versus n to be 100, for the Sn one, my bottom is n to the fourth, and that's going a lot bigger, a lot faster than the n squared are in the other two. The mn and tn are simpler ones to calculate and set up, but they are not as good as the more complicated Simpson's rule. And that's a general theme you'll see as you keep doing more and more things in math or pretty much anything. If you put more effort into how you set the approximation, you will get a better result at the end of it. So the point here is as long as these are set up the appropriate way, then we see that I can determine what my error is going to be given a certain situation. And here are the formulas you need for the error bounds, and we'll see how they apply here in a second. So I want to use numerical integration to compute the integral from 0 to 2 of root 1 plus x squared dx. This is something you could do manually if you wanted to, because that's a trig sub, that's one that you could work out pretty straightforward. How many terms would I need to guarantee my approximation is accurate to within 0.01 using all 3 rules? This is where I want to use the error bounds to tell me what my n needs to be to get me within 0.01. So what do I need to apply the error bounds? I need these k values. I need k2 and k4. I need to know b minus a, but this is just 2 minus 0, which is 2. And then I need my formulas. So to find the k, I need to take derivatives of this function. So my f here is root 1 plus x squared. And if I take derivatives, you'll see the following. We'll see that the second derivative is 1 over 1 plus x squared to the 3 halves. And the fourth derivative is 3 times 4x squared minus 1 over 1 plus x squared to the 7 halves. Now, I need to pick a number that's bigger than f double prime on all of 0 to 2. Well, that number should be 1 because this thing's always less than 1. So f double prime is always less than 1, so I can pick k2 to be 1. And for the fourth derivative here, I can use 3. It's going to be 3 when I plug in 0, and it's not going to get bigger because of how the denominator and numerator scale. So that gives me my setup. Let's see what that gives us for our errors. So for our error for the midpoint rule, this was given by k2 b minus a cubed over 24n squared. And I want this to be no more than 0.01. So I know k2 I can take to be 1, b minus a is 2, and then 24n squared. So that means n squared should be something like 100, moving the 0.01 over, times 8 over 24, which is 100 over 3. And if I square root that, I get like 5.77. So for midpoint, I would then need 6 rectangles to get this error bound. What about the other two? Well, for a trapezoid, my setup's almost the same. I just have a 12 instead of a 24 in my bound. The error for trapezoids is going to be k2 b minus a cubed over 12n squared to be 0.01. I can solve this out again. I'll get n squared is going to be now 200 over 3. And if I square root that, I get n is around 8.165. And so for trapezoids, I actually need 9 trapezoids to make this work out inside this bound. Now, what about Simpson's rule? Well, my error for Simpson's rule was k4 b minus a to the 5th over 180 n to the 4th. I want this to be around 0.01. So k4 was 3. This should be 32 because it's 2 to the 5th over 180 n to the 4th being 0.01. Tells me that n to the 4th needs to be 100 times 96 over 180, which is 160 over 3. And if I square root that, I get 7.30, which means I need 8 points to do this, which really only gives me 4 parabolas. So in this case, we don't really see that the Simpsons rule is that much better. But as you make your error bound smaller and smaller and smaller, you'll get better results here with Simpson's rule than the other two. If you want to try this again, plug in something like 0.0001 and see what that gives you. It's going to be a lot less with Simpson than it is with the other rules. So that's the idea of error bounds. The idea of being, what can I say about how off my approximation is, and is that good enough for a given problem I'm trying to solve? It's important to have these in mind when you're trying to use these numerical integrals to solve physical problems, to make sure you're accurate enough so that you don't cause any issues with other stuff you're doing further down the line with these problems.